let's take a look at what we have from last time. And we have the what? Okay. Okay, good. Calm down, please. Okay, good. So from the last times we have the forward substitution and backward substitution. Let me just write that down for you. Are you okay? Okay. Okay, it works. And so let us take a look at the we have the backward forward things. That is for the if this is lower triangular matrix, and then we would use the forward precisions procedures. And then if this one is up and right triangular, and then we would use the backwards from the bottom to the top. And this is the things we have. And this is the forward substitution. And this is the backward substitution process. And I'm going to write that down, one of the substitution, because they are symmetric, and I'm going to just do the computation operations count for just one of the process here. And let's say, for examples, we have the backward procedure. This disconnected is quite awkward. It works again. Hey guys. Okay. Okay, let's wait for 1 minute. Okay, wake up. Okay. Let's count for the one of the process here, and let me just write that formula down. And we have the let's say this is the forward substitution, and then we have xi, and then it equals to the bi, and then minus sigma sum, and then j equals to 1, and then I minus 1, and then aij xj, and then divided by aii. And this is the formula we use to calculate the solution. And this I is from the 1 and then to the n. So let's count how many operations do we need here. So for the I index here, and then how many operations do we need? So for the multiplication, we got multiplication. How many multiplications do we have here? We have I minus 1 multiplication. Does it make sense? And we have how many subtractions or additions we have here? Additions or subtractions we have here? Subtractions. How many subtractions or additions we have here? We have I minus 1. Additions and subtraction, because you will see there are I minus 1 items here, and then so add this one to this one, and then we have I items here. And then so the addition and subtractions among these items are the number of the addition and subtractions among these items are I minus 1. Does it make sense? So we have I minus 2 addition here, and then there's a subtraction here. So in total, we have additions or subtractions I minus 1 times. So there is another things here, that is the division, just 1. And that is results at the top, and then divided by the denominator here. Does that make sense? So for the I index, how many operations do we have? We have we have, actually I need to separate these two things. Because I'm going to separate these two things here because as you can see in the computer, addition subtractions is obviously easier than the multiplication and divisions, right? And I'm going to separate these things to here for the count. So for the additions and subtractions, so in total, for all the for getting the, so in total, so what do we have? How many in total? How many subtractions or additions do we have? And how many multiplications do we have? And how many divisions do we have? So we are going to sum up for the for these things. Sigma sums I equals to 1 and then to the n and then I minus 1, and which means that we have 1 plus 2 plus and then plus to the n and then minus n here. And then I believe this one should be 1 plus n and then times n and then divided by 2 and then minus n, which means that we have n squared over 2 and then minus n here. And this is the multiplications we have. How many additions and subtractions we have here? And that is we are doing the same thing, additions and subtractions. Here we have subtractions, and then that is sigma sum I equals 1 and then to the n I minus 1, because for each I index, and then we have I minus 1 addition and subtractions operations. So we are going to do the summations of the number here. And then once again, we have for the addition and subtractions, we have the n squared minus n divided by 2. And for the division here, how many divisions do we have is sigma sum I equals to 1 and then to the n, and then do the summations for the one number. And then we have n number, n once here, so it's n. So which means that at the end of the day, you are going to, if you want to use the forward substitution to calculate that solution, and then you need to do n squared minus n divided by 2 multiplication, and then this is the number of the addition subtractions you are doing, and then this is the divisions you are doing for that solutions process. And I count the numbers separately because the multiplications, addition, subtraction, and divisions, they take different time in the computer to finish that operation. Does that make sense? And we are not going to calculate, do the summations all together. Although some people will do this, but in the computer, it takes different time to finish the calculation here. And this is how we count the number of the operation. And we are going to talk about the number of operations we need in the next sessions as well. And that's for the another solutions process. And so this one is something you have already learned in the linear algebra class, although some of the students in our class forgot what it is. And this is the Gaussian elimination process. Gaussian elimination process. So let me just try to try to be nice. Be nice to me. Okay, good. Okay, Gaussian elimination process, and then it's still to solve the linear system equation, but here the system could be so if we go back to what we have just now, and then you will see I haven't shared my screen. Okay, let me just record the video. And this is the Gaussian elimination process. And then if we go back to the previous two, and then you will find that these two are the simple system, and then either we have the lower triangular matrix, and then either we have a upper right triangular matrix. And the question is that if we have a general case, and then what should we do? And that is the Gaussian elimination process. Of course, you can calculate the A inverse, but once again, A inverse it takes a lot of time to calculate that A inverse. So we better go to the Gaussian animations to get the solution of the AX equals to B. That is the linear system equation. And we are going to solve this linear system equation. And let me give you one inspiration example here. So for example, we have the E1, and that is equation 1. And I've got x1 plus x2 plus x3, and then equals to 3. And I have the equation 2 here, and then equation 2 is once again x1 plus x2 plus 2x3, and then it equals to 5. Equation 3, I have the equation 3 here, x1 plus 2x2, and then plus the x3 here, and that equals to 4. And we use 3 operations here to simplify this system of linear equation. It looks like we have coefficients here. We have all the coefficients for all the places here, and then we are going to simplify this linear system equation to the simplified linear system equations system as before. So we have the lower left triangular matrix, and then we have the upper right triangular matrix, and we are going to use the Gaussian eliminations process and use some operation here to simplify the systems to be lower triangular or upper right triangular. And so what we are going to do, so we are going to use some operation here, and it could be, so first is the scale. So use the scale multiplication, and which means that multiplication, and which means that we can do, so for the equation I, and then we can use the lambda, this is a constant. This one is a constant. We use a constant to multiply that equation and then to replace that original equation. This is the things, and then this is one operations we are going to consider, and then there is another operations we are going to consider. That is the summations or additions. So we can do this. We can use the equations the I equation, and then the lambda times the J equation, and then we do such an summation here, and then to replace the original equation I. And we can also do the third operation here, and then that is the exchange. We can exchange the order of the equation I and then equation J, and that is, we just switch the order. And the goal, what's the goal? We are going to change the system of the equation here to the lower triangular matrix or the upper right triangular matrix. And this is our goal. We want to change the things to the to looks like this, either lower triangular or upper right triangular. And so now we are going to use such 3 operations, and then to get the goal here. And then what can we do? So first of all, let's see. So for the step 1, and then I'm going to use the row 1, Actually, I'm going to get this one. My goal for this Gaussian animation, I'm going to get this upper right triangular. And so for the step one, the idea is easy. So I'm going to get this part to be 0, get this part to be 0. And let me see. So I'm going to get I'm going to change the equation to here, and then by this, by using the information in the equation 1. So I'm going to use equation 2, and then subtract the 1, and then this is the constant, and then times the E1. And then with this result, I'm going to replace our original equations to here. So what can I get at the end? Which means that for the equation 2, on the left-hand side, I got x1 plus x2 plus 2x3. And for the left-hand side of the equations 1, I got just 1, and then times x1 plus x2 plus x3. And what about the right-hand side? Right-hand side, once again, is the equation 2, right-hand side. And then minus the 1 times the right-hand side of the equation 1. So at the end, let's see, what do we have? We have x1 can be canceled by x1 can be canceled here with this one. X2 can be canceled. And so for the x3, this is 2x3, this is 1x3. So on the on the left-hand side, I got x3. Yeah, this is x3, and then equation equals to 2 on the right-hand side. And this is our new equations 2. And for the step 2, and then we are going to use the equation 1 to eliminate the variable here, the x1 variable here in the equation 3. We are going to use the equation 1 to eliminate this, to make this one disappear from the equation 3. So what I'm going to do, so if you take a look at the step 1 result, and then this is the new equation 2, right? And then we just make the x1 disappear. And then we also make, this is the side product. We also make the x2 disappear from the equation 2. So in the step 2, our goal is to make these terms disappear by using the equation 1 here, the equation 1 information here. So what I'm going to do for the step 2 is to, so this is the, I'm going to change the equation 3. So I'm writing down the equation 3 here. I subtract 1 and then times the equation 1 here, and replace, I'm going to use the result here to replace the equation 3. And let's see, what do we have here? On the left-hand side of the equation 3, we have x1 plus qx2 plus x3. And on the left-hand side of the equation 1, I got x1 plus x2 plus x3. And on the right-hand side, we have, on the right-hand side of the equation 3, we have 4. And then on the right-hand side of the equation 1, we have 1 times 3. And so what do we have at the end? So this is our new equation 3. This is 3, not B. This is equation 3, in case you read it wrong. So this one, on the left-hand side, we got, we are going to do the calculations on the left-hand side, and then we got x2. And then on the right-hand side, we got x equals 1. So this is the step 2. And if you compare the original equation 3 and then the new equation 3, you will find out that the equation, the x1 variable in the equation 3 just disappeared. And this is the things we want. We want to create out this one. And now let me write down the new system of the equation here. And the new system equation, it looks like this. It just changed to, so this is the new equation to, it becomes to x2, and then x3 equals to 2. This is the new equation up to the step. And then step 2, and then we got the, what we get? We get x2, and then equals to 1. And this is the new equation. But let's compare to what we have. I'll go, and then what we have. And this is what we have here. And our goal is right, upper right. And this is the upper right triangular. And this does not look nice. This is not the upper right triangular. So what we did here is to use the operation 3. Exchange row. And so what we are going to do is to exchange the row. Step 3. Step 3 is change the row, the equation 2, and the equation 3. And so if I just change the position here, and then I'm going to move this up and then move this down, and I got this. I got, I'm going to move this. First, I'm going to move it here. Go back. There's 1 here. It's not moving. Move. And then this is going to the bottom. Please move the 2. Okay, this is to the bottom, and then this is going to 1 place up. Okay, that looks nice. And then this would become our new equation 2, and then new equations 3. That's what we have here. It looks very nice. This is what we want to get at the end of the day. So this one is an upper right triangular. Does that make sense? So the whole process is just this one. And then this is the operations you need to do the operation, the row operation here. And then we get the desired matrix. And then once you get this desired matrix, this is the upper right triangular, right? And then you can use the process we mentioned before and then solve this linear system backward. This is the Gaussian animations process. And actually, we people would use the matrix to represent all this row operation here. So let's see. And I'm going to show you the matrix format of this of the whole process here. This is called Gaussian elimination. And the elimination, it means that you are going to eliminate the element below the diagonal. And that is below the diagonal here. You're going to eliminate all the elements here by the row operation, this 3 basic row operation here. I'm going to show you the corresponding matrix format here. And in your homework, you can use this matrix format to represent to write your answer, because the matrix format is it takes less time to write down your answer, and it's a simplified version of the representation. So let's see the matrix format of the Gaussian eliminations process. So first of all, let me remind you of the what we have at the very beginning. We have the example looks like this. We have equation 1, x1 plus the x2 plus x3 equals to 3. I'm not going to read it. This is an AI job. You know that you can open one textbook or book, and then nowadays, and then you can, the AI can read the book for you. You know that? You have the book, and then you don't need to read it. You just need to press the button, listen to the book. So I hope you can use this one. You use this function, benefits from the AI. I love to listening to the books when I doing gym. So this is a good things, the AI things. Oh, let's go back to here. So this is the equation we have, and now we are going to use the Gaussian animations, but matrix format to do the whole process again. So first, we are going to get the Gaussian, the matrix format for this linear equation. And on the left-hand side, and I'm going to create things looks like this. And then I'm going to draw one vertical line here. And on the left-hand side, I'm going to write down all the coefficients. I'm going to write down all the coefficients here from the left-hand side to this part. And so for the coefficients for the first row, I got 1, 1, 1, and then 1, 1, 2, and then 1, 2, 1, and then 3, 5, 4. And this is the augmented. So we call this, so this is the format. Let me see. This is the, what's the format here? So this is a linear system equation, and then I put the A matrix on the left, and then I use the vertical line here, and then the B is the right-hand side, and this is, we call this one is the augmented matrix. And now we got the augmented matrix, and we are going to back to the Gaussian animations process. And you would do, okay, for the step 1, and then you are going to, let's go back to take a look at the row 1, the step 1 is just use the row 2 and then subtract the 1 times the row 1, and then to replace the row 2, the original row 2. And for the step 2, and then we are going to use the row 3, and then minus the 1 times the row 1, and then replace the original row 3. And then in the step 3, and then we are going to do the row 2, and then row 3 is changed. And if you do the calculations or the computations with the matrix format, and you will immediately get this one. So for the step 1, and then the results, you can write them in this way. For the row 1, for the step 1, and then you would get 1, 1, 1, 3. Let me see, this one, it should be 0, 0, 1, and then 2, and then 1, 2, 1, 4. And this is the results for the step 1. And then for the step 2, you would get 1, 1, 1, 0, 0, 1, because we are not changing the row 1 and row 2 in the step 2, and then we just change the row 3 here. And then this is the row 3, the step 2 result. And for the step 3, and then we get 1, 1, 1, and then 3 here. And then we are just exchanging the row 2 and row 3. So which means that the row 2 is here, the original row 2 here is here. The original row 3 will become our new row 2, and then this one, and then that is the result. And if you take a look at the matrix format, is quite, the things is so simple, and then it looks very compact. So if we use the matrix format, use the matrix format to do the Gaussian animations. And this is the things, and let me see. I am going to show you one more example, and then, but before this is the basic example. And then I'm going to give you one general situation. And that's general situation is that, so for the general situation, and then what should we do for each step? The general situation. Situation. For the general situation, we have, let's say we have this system of equation, A11x1, A12x2, plus all the way to A1n xn. And you notice that in the example 1, we just have a 3 by 3 matrix, but now we have an n by n matrix. And this is the first row, the first equation, A21x1, A22x2, and then plus all the way to the A2n xn and B2. And we have an equation here, an1x1, an2x2, plus all the way to the ann xn bm. And once again, we prefer the augmented matrix format. The matrix format looks like this. So the matrix format, it should be the A on the left and then B on the right. So what I got is A11, A12, and then A1n. And then this is on the left, A21, A22. This is the second row. And AN1, AN2, and then ANN. This is the last row. And on the right-hand side, you got B1, B2, and then Bn. And this is the augmented matrix. And what do we need to do for each step? Well, so that's not too good. I'm going to use, let me see. I'm going to just write the algorithm down, but you don't need to copy down this because it's on your lecture notes. Okay. And I'm going to write down the algorithm here. The algorithm here is, so this one is a Gaussian elimination algorithm. And it's on your lecture notes. And you don't need to memorize all these things. It's on your lecture notes. So for the step 1, and it's just the index sum. So for the I equals to 1 and then to the n minus 1, and let's do this step 2 to the 4. So for each index, and then we are going to eliminate the elements below the diagonals in the I column. So for each I, and this is the remark here, for each I iteration, I iteration, and then we are going to eliminate the I column elements, below the diagonal. And because we are going to get the upper right triangular matrix, so for each iteration, and then we are going to eliminate the I columns elements below the diagonal. So for examples, for the iterations I equals to 1, and then for the iteration I equals to 1, and then we are going to eliminate all these elements to 0. And for the I equals to 2, we are going to work on the second column, and then we are going to, this is the diagonal, and then for the second iteration, I equals to 2, and then we are going to eliminate all these elements to 0, because these are the elements below the diagonals in the second row. Does that make sense? So for each iteration, we are doing this. We are going to eliminate the elements below the diagonal 1 by 1, and then because this one we need to keep it, So there's no I equals to n here. We just need to eliminate the a minus one column elements below the diagonal field. And this is the things we have just n minus one iteration. And then so for each iteration, we would do the step 2, step 3, step 4, and then what's in the step 2? In the step 2, we are going to choose the so let P be the smallest integer with I smaller than or equals to P and smaller than or equals to N, and the API, and then that's not equals to 0. And then this is, we are working on the I column, and then we are finding the first, so which means that this is the first non-zero elements in that column. The first non-zero in the I column. And this is the things we find the first non-zero elements in the I column. And if no such an P, no such an integer P can be found, then what should we do? And we are going to just output, and then output no unique solution. Is this. And we stop the iteration here. And this is the step 2. And if this happens, if we have the P, and then we have the number P, and then what we are going to do is doing the switch. If the P does not equal to I, and then, or if the P equals to I, and then we are not doing anything, but if the P does not equals to I, and then we would do the switch. We would switch the row P and the row I. And I will explain the idea later, and then I'm just introducing the algorithm a little bit first. For the step 4, after the row is changed, and then what we would do is, so we have a non-zero elements here, and then we would do I plus 1, and then to the end, and then we would do the step 5 and 6. And for the steps 5 and 6, and then what we do here is just the low mode eliminations process here. And then we are going to set the ratio Rij, and then equals to the Aj, and then divided by the Aii. And then the step 6 is just to get the new value for the row J, and then that is the row J, Iij, and then times the EI, and then with this result, and then we are going to replace it with the replace the original EJ, and then get the new row J. And this is the things, and then this is the step 2 and step 4, and then after you perform the n-1 iteration, and then we would go to the step 5, and then if the ANN equals to 0, then we would output again. This one, there's no unique solution. And this is the things, and then up to the output, and then we will stop here. And let's see, why do we have such a things here? And that's because if you take a look at the step 2 and then step 3, actually this one is preparing for the row eliminations process. And so let's see what we have here for the step 2 and step 3. Let's say after the one iteration, and then you get to this. Let's say up to one iteration, you get to, so let's say, let's say we, up to one iteration, this is the original one, right? A11, and then A12, and then A2N. And let's say now what you have is, this one is 0. And then this is A21, A22, and then A2N. This is A1N. So if you take a look at the row animation here, this is the step 4. The step 4 is using, what's the ratio? The ratio definitions, it looks like this. It's the ratio definition is the AJI. This is the I column, and then this is a J row, and then this is AII. So for examples, we are working on the first situation, and then the I is just equals to, I believe there's something wrong here in my index. It should be AIJ. Yes, there's something wrong in my index here. It should be the AIJ. No, it should be the first column and then J row. It is not wrong. But here, if you take a look at this one in the denominator, it is AII. And for the first iteration, if we want to do the first iteration, and then I equals to 1 for this matrix, and then what do you have? What do you have for the, let's say J, because I equals to 1, and then the first J equals to 2, right? And let's say, let's calculate the first ratio, and J equals to 2. And let's say, see what is the R12. R12 is just a A21 divided by the A11. And A21, let's say it's non-zero, and then this is A21. But for this matrix, your A11 is 0. So do you see anything wrong here? The denominator is 0. So we need to do some things before we go into the step 4. In the step 4, we are just doing some row animations as we saw in the basic example, but there's one exception here. If you have, for the diagonal element here, you have a 0 here, then this is not defined because we cannot have the denominator as 0. So what we need to do is to find, so go down to find a non-zero here in this column, and then the first non-zero element you meet, and then you just stop here. And then let's say this A21 is non-zero. Then we need to switch the row, and then get this one to be our A11, the new A11, switch the row. And this is what we did here for the step 2. So step 2 and step 3. And we are going to find the first non-zero item, and let's say the A21 does not equal to 0 for this example. And we are going to exchange the row 1 and row 2, and then this is our new matrix, but the index is a little bit confused, but this is the B vector here on the right hand side. And then now we are going to make the first row down here, A2N, A31, A32, and A3N, AN1. and AN2, ANN. So now if you do the rows right here, row exchange here, exchange the row 1 and row 2, exchange the row 1 and row 2, and then now you can use this first row to eliminate all this element to be 0. Does that make sense? So the idea is that if you have the 0 on the diagonal, and then you are going to do some row exchange here, and then to find the first non-zero elements in the same column, and then exchange these two rows. And this is the idea for the step 2 and step 3. And there's one more information here from the step 2. If there's such an integer p, such an integer p cannot be found, and then we can say there's no unique solution. And then why is this? So this is saying, so for example, this is the iteration 1, then the step 2 iteration, that exceptions is, so another example here, which means that first you would have all the 0 here in the first column, because you cannot find a non-zero element there. And this is A12 and then A1n. And then ANN. AN2. So it's obvious that this one, the A matrix is singular in this one. So this one, the singular, A is singular. And hence, no unique solution. Does that make sense? So because for the step 2, there's one outsider. There's one outsider here. And then it's a P. We cannot find such a P. And then which means that all these numbers from I, the index from I to N, and then they are all 0. They are all 0. We cannot find a non-zero element here. This is the case for the first situation. And then if you cannot find any non-zero element in the first column, and then this is the case. And then you have all the 0 here for the coefficients for the x1, and then which means that this system is singular. And then your x1 can be any value, right? And then so there is no unique solution. So this is algebra, and then for the step 2 and then step 3, it's just do some pre-processing before the step 4. And then this step 4 is actually doing the row elimination things. And this is the things, and then for the ANN, there's another exception here, the step 4, step 5. And after the animation, and then ANN could be 0. And then for that case, the XN can be any number. So for the step 5 here, it catch another exception here, and then it says no unique solution because the XN can be any number in this case. Does it make sense? Any questions? If you don't have any question, then let's go to one example. No more example because it's 11:50. And I'm going to go for another examples next time. It's a 4x4 matrix. That's good. And we will count the operations for the Gaussian eliminations next time as well. Oops. 今天讲的，今天讲这个对吧？今天讲的啊，明天上次讲的example会讲。然后最早这个，然后今天有找我4点到5点。啊？结果找我。哦，对，4点到5点。